Space travel is often compared to climbing a tree. The ascent is a massive engineering feat, but coming down is as simple as letting go. Of course, allowing gravity to handle the entire descent results in a near 100% probability of death. This scale model reveals the core problem. The International Space Station is screaming sideways at a staggering 28,000 kilometers per hour. Right here, attached to the Russian segment, is the Soyuz. This is the vehicle tasked with bleeding off all that energy. Engineers have roughly 3.5 hours to take that 28,000 km/h velocity and bring it to a dead stop. Success requires a highly choreographed sequence of braking maneuvers designed to survive the brutal laws of physics. The process begins at a crawl. The capsule detaches and drifts away from the station at just 12 to 15 centimeters per second to avoid a catastrophic collision. Once clear, the crew initiates the deorbit burn. The spacecraft fires its thrusters against its direction of travel. Precision is everything. A weak burn skips off the atmosphere. Conversely, an overly powerful burn generates enough friction to incinerate a capsule. The single calculated engine burst is the only thing dictating a safe path through the outer atmosphere. Minutes before impact, the Soyuz jettisons its extra modules, leaving only the heat-shielded descent module to face the transition. This is break number 2, atmospheric drag. Hitting air particles at orbital speeds feels like slamming into a wall. The friction becomes so intense that the surrounding air superheats, transforming into a layer of glowing plasma. This plasma envelope blocks all radio waves, creating a total communication blackout. For several minutes, mission control can only wait and watch silent screens. But the thin air is an incredible break. In just 8 minutes, the capsule's velocity drops from 28,000 km/h to just 800. Engineers effectively use the atmosphere as an invisible net to absorb the spacecraft's massive kinetic energy. At 10.5 kilometers above the surface, the air becomes too thin to slow the 800 km/h capsule any further. This triggers break number 3, the parachutes. They deploy in a staggered sequence to prevent the main canopy from being shredded by the remaining speed. The main parachute successfully bleeds the speed down to 22 km/h. However, hitting solid ground at 22 km/h would still cause severe skeletal injuries to the astronauts inside. Just 70 centimeters before impact, break number 4 activates. 6 retro rockets fire simultaneously to drop the landing speed to a survivable 5 km/h. Reaching the ground is a seamless baton pass of physics, shifting from orbital mechanics to aerodynamics, and finally to explosive chemical braking. While the capsule survives the exterior heat, the astronauts inside must endure the brutal physical reality of rapid deceleration. After months of weightlessness, the sudden return of gravity, magnified to 4 Gs, feels like a crushing weight on the chest and limbs. The physical evidence of this journey is visible on the capsule itself. This heavily charred, blackened exterior shows the extreme thermal stress required to keep the crew safe. Upon extraction, astronauts are often physically incapacitated. This image captures the exhaustion and the immense joy of surviving the fall. Their brains must even relearn basic physics. It is common for them to drop objects in midair, momentarily forgetting that things no longer float. Leaving Earth requires explosive power, but coming home requires zero-margin precision. Knowing the risks of the descent, would you take the journey? Tell us in the comments and subscribe.